All right, let's get into one of the all-time classic papers in computational science. And seriously, the title alone tells you you're in for a treat. 19 Dubious Ways to Compute the Exponential of a Matrix. It was written way back in 1978 by Cleve Moeller and Charles Van Loan, and it's basically a detective story about a problem that looks super simple on the surface, but is just loaded with hidden traps.
You know, every great mystery starts with something that seems totally normal, almost boring. And for us, our story starts with a concept you probably first saw back in high school math class.
I'm talking about the exponential function, e to the power of x. For any single number, figuring this out is a piece of cake. Our calculators do it in a blink. It's predictable, it's well-behaved, it's just fundamental. But what happens when we swap out that simple little x for a whole matrix? And don't let the math here scare you. This isn't just some abstract curiosity. The matrix exponential is the absolute key to solving systems of linear differential equations. And those are the language we use to describe pretty much everything, from the circuits in your phone to how animal populations grow and shrink. And look at that definition. It looks exactly like the one for a single number, just a clean, simple, infinite power series.
So you'd think, right, with a beautiful definition like that and all these critical uses, calculating it should be a solved problem. It should be totally straightforward, shouldn't it?
Well, as you can probably guess from the title of the paper, the reality is anything but simple. This is where our nice, neat little story takes a sharp left turn.
And the authors just lay it all out there, right in the abstract. They looked at all these different methods, and their conclusion was, honestly, kind of shocking. Not a single one was perfect. Every single one had a fatal flaw. But hold on, what does it even mean for an algorithm to be satisfactory anyway?
Well, the authors came up with this 5-point checklist. First, an algorithm's got to be general. It needs to work for all kinds of matrices, not just the easy ones. It has to be reliable. It should raise a flag when it knows it's about to give you garbage. It must be stable, which means it doesn't make tiny errors blow up. And of course, it needs to be accurate and efficient. The problem is, no method gets a perfect score. You always have to give up something.
So let's go on a little tour of a couple of these dubious methods to see exactly how they fall apart. And we're going to start with the most obvious approach you could possibly think of.
Method number one, just use the definition. I mean, it's right there. You just start adding up the terms of that power series, the identity matrix plus a squared over 2, and so on, and you just keep going until your answer stops changing. It seems completely foolproof.
To put this to the test, the authors cooked up this seemingly innocent little 2x2 matrix. Okay, the numbers are a little big, but it's just a simple matrix. I mean, what could possibly go wrong?
Oh, just everything. On the left is the answer the Taylor series gives you, and on the right, that's the actual correct answer. This isn't just a little bit off. This is a total, unmitigated disaster. The numbers aren't just wrong. Some of them even have the wrong sign.
So why did it fail so spectacularly? This is a classic problem in computing, and it has an amazing name: catastrophic cancellation. See, in the middle of the calculation, some of the terms got huge. We're talking numbers bigger than 1,000,000. But the final answer has tiny numbers, close to 1. So when the computer tried to add and subtract these massive numbers to get a tiny result, it's like trying to measure a grain of sand by weighing a mountain with it and without it. All the important little digits just got wiped out, leaving behind pure numerical garbage.
Okay, so the direct approach was a bust. Let's get more clever. Let's try a more elegant, theoretical approach using eigenvalues. The idea here is to break the matrix A down into its basic parts. You find its eigenvectors, that's the matrix V, and its eigenvalues, which make up that diagonal matrix D. Calculating the exponential of D is super easy, and then you just piece it all back together.
This looks like a genius shortcut, right? We're avoiding that whole messy, infinite series thing. It feels like we totally outsmarted the problem. But remember the rule. Every single method has a flaw. So what's the catch this time?
The catch is hiding in that little v inverse term. If your matrix A has eigenvectors that are almost pointing in the same direction, your V matrix becomes what we call ill-conditioned. The best way to think about it is like trying to stand on a very wobbly chair. The tiniest little nudge and the whole thing comes crashing down. That's an ill-conditioned matrix. It's incredibly sensitive.
And that sensitivity is where it all falls apart. An ill-conditioned matrix acts like a giant amplifier for any error.
Even the tiny, unavoidable rounding errors that happen just from storing numbers in a computer get magnified by a ridiculous amount when you try to calculate that V-inverse. You end up with another answer that's completely wrong, but for a totally different reason than our first attempt. So we've seen two totally different methods fail in two completely different ways. And that brings us right to the heart of what this paper is really all about.
This table really just lays out the whole dilemma. You've got your series methods. They're simple, but as we saw, they can blow up with round-off errors. Then there are the clever decomposition methods. They look great on paper, but they can be super unstable if your matrix is ill-conditioned. And finally, you can use general-purpose ODE solvers. These are pretty reliable, but they are often brutally slow and inefficient.
And that leads us to the big conclusion of the paper. There is no silver bullet. There's no single best algorithm for computing the matrix exponential. The right choice is a moving target. It completely depends on the specific matrix you're dealing with at that moment.
But honestly, this story is about so much more than just one mathematical function. It's a perfect lesson in the hidden challenges that pop up all over scientific computing.
Take a look at this hump phenomenon. For certain matrices, the answer can shoot up to some gigantic value before it eventually settles back down to a small one. Any algorithm you use has to somehow navigate this giant hump, and it's a minefield. If the numbers at the top get too big, your computer just gives up. That's an overflow error. But if you try to calculate the tiny value at the end, you run right back into that catastrophic cancellation we saw before.
Now, one of the most popular methods today tries a really clever trick to get around this. It's called scaling and squaring. The big idea is to basically tunnel under that dangerous hump. You take your matrix and divide it by a big number, say 1024. Then you compute the exponential of that new tiny matrix, which is much safer. And then you just square the result 10 times to get back to your original answer.
It sounds like a genius solution, right? A perfect workaround. But you have to ask the question, what happens to that tiny, unavoidable little error that creeps in when you calculate that first small step?
And here it is, the final devastating catch. When you square your result over and over again, you're also squaring the error over and over again. A tiny, insignificant error at the beginning can grow exponentially, completely poisoning your final answer. This constant battle between an elegant mathematical idea and the messy reality of how computers actually handle numbers, that is the absolute heart of numerical analysis.
But all of this brings us to one last big question. This paper is from 1978. We have computers now that are literally millions of times more powerful. Surely we've solved this problem by now, right?
And the answer, fascinatingly, is yes and no. Today's algorithms are way more sophisticated. We have clever hybrid methods that try to pick the best strategy for any given matrix. But the fundamental trade-offs, the core dilemmas that Mahler and Van Loon pointed out all those years ago, they are still with us. There is still no single perfect method. And that is why this paper about dubious ways to do something is still one of the most important, most cited works in the entire field, a timeless lesson on the beautiful, frustrating art of computation.